So I want to start by thanking again the organizers, Charles and June, for putting together this very interesting workshop. My presentation is mostly going to be about giving an introduction to what is Bayesian methods or Bayesian inference, or Charles called it a Bayesian probabilistic framework. So I'm with the Math and Stats department at the University of New Mexico in Albuquerque, and taking advantage of this, I'm going to start by pointing out what are some of my interests. So Bayesian method, which is what this presentation is going to be about. Hierarchical models, which I'll talk a little bit about hierarchical models, but there's going to be more. Oh, do you want me to use the? You want me to use this one? Okay. I'll also do some work on time series analyses, which I'll mention in the computer lab session, but not as much in the talk. So, for example, here this here is part of my dissertation work, which is doing a latent structure decomposition of the SOI into various components, some representing a signal and other ones representing noise. And I also do quite a bit of what is called Markov chain Monte Carlo simulation, MCMC simulation. And this is this example down here has to do with calibration of a surrogate climate model, which is something I'm going to mention. This is work with Charles, who was here and is our organizer. Okay, so first part of the presentation is going to be kind of like a tutorial about Bayes. For those of you that is the first time that have seen this, and then the second part is going to be mostly my work related to climate on using Bayesian approaches. So I start by pointing out that the whole thing about Bayes started Bayesian started with Thomas Bayes, and in particular his posthumous essay was a particular case of what is now known as inverse probability, or finding the probability of a hypothesis being true given some evidence, and using what is called Bayes formula or Bayes theorem to obtain that through probability of the evidence given the hypothesis times our prior probability of the hypothesis over the probability of the evidence. So, oh, by the way, these slides are already up on our webpage, on our conference webpage, but I made a few changes here and there, so I will update the slides. Okay, and so one of the problem that Bayes was working on is this one, where just simple math problem where you say you have x being the number of times an event has occurred, theta the probability of occurrence, and then kind of the question is to find the probability that theta is in this interval given that we observe x. So assuming that there's some independence occurrences, that leads into what is called a binomial distribution or a probability distribution of x given this theta probability. So in this paper about Bayes, it is mentioned this billiard table, which essentially devises a random mechanism for theta occurring with equal probabilities over the interval 0, 1. So in other words, this is what we're going to call as our prior distribution. So theta being a uniform on the 0, 1 interval, and therefore if we observe x, then we compute the probability of theta given x with Bayes formula. This is the so-called posterior probability distribution, and in this case this turns out to be proportional, assuming uniform prior is just proportional to this expression and that is what do we know the likelihood function in this problem. It corresponds to what we know as a beta, kind of a beta distribution, alpha, with this parameters. So instead of starting with a uniform, we could have used, say, other beta distribution, and still posterior would also correspond to another beta with parameters alpha plus x, beta plus n minus x. So certainly the prior is a subjective choice that tries to express our knowledge about some quantity of interest. So parameter of interest in climate could be some climate model parameter. So this is just a quick comparison of how the posterior looks for various data choices. And I think the interesting point here is to notice that as more data is collected, this posterior tends to be centered more around some parameter value and looks more like a kind of like a Gaussian distribution. So in the lab session, we're going to be using some R. So this is how one could answer this question about posterior probability of theta being in some interval for this particular example using some R code. So it's considering 3 different priors: beta 1,1, beta 0.5, 0.5, which is known as Jeffrey's prior in this problem, and then a bit of a more informative prior, which is a beta 4,4 distribution. And then here we're just looking at the different resulting probabilities using this p beta function, which is just the probability under this beta distribution. Then another thing we're showing here is that we use quite a bit in Bayesian inference are like probability intervals around the quantity of interest. So it depends on quantiles of our distribution, our target distribution.
So you will probably have to provide more of an explanation of what this problem is solving. Will you do that later, or?
In terms,
I wasn't clear on the problem. The billiard problem?
Oh, okay.
Is that the problem you're solving?
The problem we're solving is just trying to find what is this probability. Okay? What is the probability that theta is between 2 numbers for a situation where you have number of times an event has occurred, for example, coin tosses, okay. And theta is just the probability of an individual coin toss. Okay? And that's it's more like a motivation of what Bayes is about. So what I was trying to say is that the starting point of Bayes was a billiard table that leads into saying that all our possibilities for this theta are uniformly distributed on the 0-1 interval. So everybody has equal chance of occurring. All thetas have equal chance. The other point I was trying to make is that it's not necessary that we use this distribution, but we could also be considering some other distributions for that. Now everything turns out to be nicely solved in this case, and I'm going to move away from that through the use of Monte Carlo, what is called Monte Carlo simulation, which here is illustrated through samples of the probability distribution, target probability for this theta parameter. Here we have the limits for a probability interval, and then instead of finding quantiles exactly, then we do some kind of Monte Carlo integration approximation by looking at all the possibilities divided over the total number of samples. Why am I referring to this? Well, because in most Bayesian problems, we're going to need to do, and like in the case of calibration of climate parameters, we're going to need to do some kind of Monte Carlo approach to find a solution, right? So So this is an example where exact solutions can be obtained, but in general, we know that most Bayesian problems are going to lead into intractable situations. The other thing I wanted to point out is a quick example of how Bayesian think about priors. So here we're saying, let's say that theta, the most favorable value is 0.6, but let's also assume that there's the quantile 95% is close to 0.5, which means that the probability that theta is below to 0.5 is equal to 0.95. And then the question I'm raising here is, can I find a distribution that would match this this original information? And we can do that, and this is the solution using again some R code where we're simply screening, considering that the mode of this distribution is 0.6, and then screening over all the possibilities, and that leads into what would be a beta 7.5. That's a match. Yes, go ahead.
What's the application of this?
That's what I'm going to move to, right? I mean, the application is essentially pointing out how one can think about a prior distribution in problems. And so if you have some information about your unknown quantities, this is one way to try to express that information through a probability model. Okay, so the purpose of this is that typically we have information a priori about something. One way, in this example, one way to try to quantify that is by doing this, which is not always easy.
So you said something about screening. That seems like an R term, right? You said screening?
Essentially, well, you have to do kind of like a numerical solution for this, and you need to consider several values of beta, and then express alpha in terms of beta to find a solution that resembles what we want, which is this equation.
Okay. So,
okay.
I'm not sure if I could understand that. Because that deals with the solution strategy, right? And you expressed it in R.
Right. It's a solution strategy, but it only works for this case. When you want to do it for other cases, then you sort of have to rewrite this again, right? I mean, it wouldn't work in general, right? It works only for this case because there's certain information about the probability model that we're considering that allows to work the solution this way. Okay. Now, if you had like a normal distribution as a prior instead of, say, beta, maybe you're thinking in terms of information about where this distribution is centered, that would give you your mean. If you're thinking about the spread of the distribution, that would give you kind of like the variance, right? So depending on your choice of a probability model, then you can find different priors. Okay, so in general, more formally, sorry. Yeah, oh, sorry, I didn't see your. Go ahead.
Okay. I was just wondering about your theta. What does it actually say? Does it change with the design?
No, theta just represents the probability of occurrence in a single trial. And it doesn't change in design because we're thinking that the trials are independent. We have independent realizations. So think of in terms of, say, a coin toss. So we simply tossing this coin, and we're assuming that the probability of occurrence is the same. Okay, so that's what theta represents.
So the distribution depends on the kind of distribution that you have.
Right, correct. It's going to depend, right, correct. What is in the distribution you have for x, for your observable quantity? Correct. So a more general So that was more like just a bit of a worn-up example of how Bayesian ideas work. And now in general, in Bayesian, we typically have an interest in some parameter vector or scalar. I'm going to call this theta. For example, some parameters of a climate model, which is one of the discussions I'm going to have later. Prior knowledge is expressed in terms of a probability model. That's P of theta. So in our previous example, this was some kind of uniform distribution. This was corresponding to the probability of one trial. And then typically we have data associated to this parameter that gives like a joint distribution for x given theta. And then the posterior or the inverse probability is the probability of this theta given this data, which is obtained through what is called Bayes' theorem or Bayes' formula of that. It essentially works through this calculation saying that the posterior is proportional to our joint distribution, which is also known as the likelihood function, times the prior. This integral down here, that's what is called the marginalization constant, which is the predictive distribution of the data. Does not depend on the parameter, and this is why Bayesians use this notation, that the posterior is proportional to a likelihood times the prior. And this is the way we go about, for example, doing calibration on CAM 3.1 with using some of Charles' experiments or Charles' output. Now, in the previous example, what I wanted to point out is it's an easy example just to show that sometimes you can get analytical solutions to this formula, but that in general does not occur. In general, what we need is some kind of Monte Carlo scheme to find a way to approximate this distribution, to generate samples from this distribution and to do approximations of this distribution. Now, some other comments here about Bayes is that this ideas were not too developed in the 50s, and in particular in terms of applications. So someone was asking about applications. There was not a lot of applications of Bayes in the 70s, and it was mostly a mathematical theory that we were looking at. And some scientists like William Feller, who was a famous probabilist in the 50s, he pointed out that essentially Bayes would not be capable of solving any applied problem, and that other theories like frequency theories would do a lot better job in doing that. Nowadays that has certainly changed quite a bit, and I think most of us accept random mechanism exists that generate different types of data. This was pointed out in the previous presentation about different types of random mechanisms. Now the Bayesian adds an extra step and thinks that parametric quantities are also random, like when we say theta follows a uniform distribution in 0, 1. So this is similar to think about fitting some kind of regression to some data. Oh, by the way, this reminds me that when I say model in my presentation, I'm thinking more in terms of a statistical model, not a climate model. I'll try to clarify that as we go along. And in particular, the turning point, I think the turning point in applications for Bayes is MCMC, Monte Carlo Markov chain, which has to do with the Gibbs sampling, which is an algorithm to generate from a probability distribution that depends on various parameters, which is done through what is known the full conditional distributions of this joint distribution. So one starts with an initial value, and then one iterates through the full conditional distributions to generate a new theta vector and repeats this algorithm over and over. And under general conditions, it can be shown that if one proceeds this way, then we can generate samples from our posterior. It looks like prior here, but I really mean any probability distribution that I want to simulate from. Then also Metropolis, working at the Los Alamos National Laboratory, he did quite a bit of computation in terms of Monte Carlo integration and developing this algorithm to deal with problems that had to do with density of states in physics. And that has taken us to what is nowadays known the Metropolis-Hastings method, where essentially one samples this theta parameter through what is known as a proposal distribution, and then performs some kind of acceptance rejection step to decide if we keep our proposed theta or otherwise reject the theta. Now, if one uses some kind of symmetric distribution, like say a Gaussian distribution here, then that becomes the Metropolis method. So the Hastings version is essentially use any arbitrary proposal density to sample the parameter space. Now it's important. One thing that is important is when one uses this type of simulation methods, one should check for acceptance rates or trace plots to assess if there's convergence. And this is something we're going to do in the tutorial session as well, as we run some MCMC and look at how that MCMC is behaving, in particular with an application of Bayesian calibration for a paleoclimate data set.
Maybe you should define calibration.
Estimation of parameters.
Okay.
Which is what I've been talking about for all this time, right? Another thing I have to mention is that, in part, Bayesian applications have expanded due now to the existence of generic software to implement Bayesian methods. So one example of that is Openbugs. Certainly R has a lot of libraries that now use Bayesian methods, but in particular I'm mentioning Openbugs because that's the software we use to solve our paleoclimate calibration problem, and is the one I'm going to be using for the computer session. So Bugs stands for Bayesian inference using Gibbs sampling. It's based on some kind of cyclical graph. This was developed in the UK at Cambridge, and a lot of it has to do with medical health type of applications for hierarchical models. The issue I have with this kind of tool is that I think it's limited for high-scale applications and for very large data sets like the ones we have in climate, in particular when we're dealing with like large atmospheric models. It's a very good tool to understand what Bayesian inference is about, and in particular for the example on paleoclimate, we use an interface of Openbugs that is called JAX, and that worked really well for our problem. So so the two components are computation and availability now of software to perform this calculations. So what does that have to do with our topic? Well, what does that have to do with climate models? So in particular, I'm mostly going to refer to an example with general circulation models. I'm also going to talk first a little bit about a surrogate example. This is joint work with Charles Jackson, who as you know, is at the Institute of Geophysics at the University of Texas in Austin. I'm not going to talk much about regional climate models. I've done a little bit of work on that, in particular looking at statistical models that allow to, and with Bayesian approaches that allow one to explain how extremes behave from a regional climate model. So when Charles approached me to work on this problem, this is the kind of the question he had in mind in terms of calibrating CAM 3.1, the community atmosphere model that has been run in NCAR. So the question was finding a posterior distribution. So now Bayes' theorem is expressed in a slightly different way, where our likelihood function, which is this expression here, depends on the metric of model skill, which we also call cost functions. It's comparing observations with climate output. Then we also have a prior on some climate parameters, and this integral here is just representing the denominator part on Bayes' theorem. So essentially, posterior is proportional to e to the minus 0.5 times this cost function times prior. So the cost function considers observations and model output, and then the strategy is based on some kind of a stochastic sampling, some kind of MCMC approach that uses some kind of a optimization approach as well. So in a paper that appeared in the Bayesian Analysis Journal, working with a former graduate student at University of New Mexico, this is Alejandro Villagran. So we considered this surrogate model that was developed by Charles that looks at surface Earth temperature anomalies at response and depends on some orbital parameters. So it's kind of like a simulation tool, right? Or more loosely speaking, it's kind of like a toy model that one can use to explore different answers and results. So in particular, the cost function for metric was a measure between observed data and model that also depended on, I think we have longitude, latitude, and seasons as well. And the three parameters here are these orbital parameters, M. And so our posterior distribution in this case, just following on the ideas of the first part of the presentation, is the likelihood, which in some ways implicitly assuming that we have Gaussian errors in this model times some kind of prior on the M parameters or our orbital parameters. So this is our main result in this example, which shows the estimated posterior probability distributions from different sampling strategies. Some of the sampling strategies are based on Monte Carlo Markov chain or adaptive Metropolis methods. And then there's this other strategy that has been used quite a bit at the Institute, which is the multiple, very fast simulated annealing, which corresponds to distributions that have wider tails in this case. They're all centered around the same place, but there's certainly differences on the spread of this probability distributions depending on the sampling method. So this very fast simulated annealing is an approach for Bayesian inversion used in geosciences and depends on some kind of cooling schedule and uses Metropolis in some way. It depends on some kind of proposal distribution, and one uses multiple starts to try to gain on algorithmic efficiency. Oh, sorry, go ahead.
I'm sorry, I missed a bit. What are the model parameters? Are these the obliquity?
Yeah, obliquity.
These are the ones which you know exactly, no?
Yes.
Yeah, and
yes.
And the metric that you use for optimization is this.
That's the metric. That's the metric that defines our that defines our likelihood.
Okay, so it's an estimation that you have. It's not the real. You don't know it for sure what
I think we.
In this case, it was you used the model to generate surface air temperature data,
Okay.
and then you use this
So-
algorithm to say what is the orbital configuration given the data
That was generated. Yes.
So it's a toy problem.
Yes. So it's like a simulation. Yes. It's a model where you simulate the observational data, and then you post-calibrate this.
But you do all the runs for all the parameters. You do that first a priori, and then afterwards you do this estimation, or is it an iterative process for the runs of the parameters?
I think it's post runs, right? We first generated the runs, and then we did the calibration, right?
You could do one run that generates the data, and then you do everything that Gabriel's talking about in terms of I guess the surrogate model, you can kind of take that off the table. It existed, but all the runs he is talking about is the part that you need to determine or to estimate the parameters in a probabilistic framework.
But you need a very long run with all the where you have the whole parameter space explored.
No, not in this case. So actually,
So in this case, the first result I showed depends on I think it depends on a very long run of the model, and this result here. But then also what we did later on, I'm going to skip a few slides here, is we compare the results of the different sampling methods just doing a short run. Sure, only doing a few runs to approximate the posterior, this posterior density. This is this picture here.
Can you explain? I mean, I think you're anticipating the use of surrogates.
Right.
So this used a surrogate, but we didn't use it in generating the probability distributions, right? It's a direct sampling.
Right. This is exploring.
The this question is
the direct.
There's some expectation that, particularly with the climate model, that you would have a surrogate in between, so you would be sampling from a surrogate.
Right. That's something I was going to mention when I get into the our results about the NCAR CAM 3.1 analysis that we have done.
So
right.
But maybe for the group, maybe hint or suggest that the difference between direct sampling and sampling from a surrogate.
Okay. Okay. Good point. Yeah. So these are all direct samples from the surrogate climate model.
I guess that makes it very confusing.
or direct samples from the model, right? This model that we have, right? This is a starting model that we were looking at. So there's, I think, as the slides I skipped were just more technical details on the different methods. So, for example, I had this slide about saying how Charles thinks about it in terms of this algorithm that I was describing. Then there's also a description of what we did using adaptive Metropolis, which essentially means that our proposal distributions to do the sampling depend on an updated covariance matrix that is based on previously sampled states. And this method, my understanding is that this approach is now used quite a bit to approximate posterior distributions from some of the European models. Is being used this, and then the delay rejection strategy, which is something that we consider first on this surrogate climate model. And the delay rejection essentially tries to make the sampling of the parameter space a bit more efficient by considering different strategies and by combining different proposal distributions. I think one interesting result on this example as well is one that has been observed in other cases, that priors are important in this type of calibration exercise, because for under different priors, one that is informative and one that is vague, we can see that posterior distributions are different. So simply using a flat prior, a complete uniform prior, as in the very introductory example, that's not always the best idea in calibrating a kind of a climate model. So you can see the difference here from using some kind of informative prior versus some kind of non-informative. Yes, go ahead.
But that contradicts one of the first slides that normally it should, under general circumstances, it should converge to the same probability. So what does it tell you about that? What does it
yeah.
It says something about the climate model, or does it say something about the statistical model?
I think it has to. In my opinion, it says something about it has to say something about the climate model. I don't know exactly what, but it doesn't quite satisfy the statistical properties that exist under independent sampling or independent replication of experiments, which is a very common property is a very common property in the statistical models. Yes, go ahead.
This is a comment really, but it could say something about the problem. So in some problems with climate models, this is definitely a feature.
Mm-hmm.
And in other problems, it's more data-led and it's not an issue.
Right. Right, and then also in the first example, the assumption is your data is going to infinity. You're capable of collecting an infinite amount of information, and therefore you can get your. But as we know, data in climate models is more limited. So we cannot presume that we have infinite amount of information to compute our posterior distribution. Do you agree with that? Do you agree with that view, Charles?
Yeah, I mean, I guess. I'm just emphasize Ben's comment, which is, if we're in a situation where a lot of things depend on the priors, that means you haven't learned very much from the model.
Mm-hmm.
And therefore, that's good to know, right?
Right.
So it's in this framework, you can learn to what extent your knowledge has been updated, right, through these experiments and or data. And there are cases where maybe you haven't learned very much, and this at least lets you know that.
Mm-hmm.
But yeah.
Okay, so I don't know, what's my time? I still have a few more.
So there's a clock up there. Do you have a clock?
I have a clock on my.
So we started about 15 minutes after.
Oh, okay.
Yeah.
Okay, good. So we still have like another 10 minutes or so, right? Okay, good. So I'm going to spend the rest of my time talking about the calibration for the community atmosphere model, which is the NCAR version. This is the 3.1. My understanding is that a more current version now is in place to do experiments with this. So these are model runs of climate simulation with physical observations. There's some inputs or parameters related to clouds and ice. One of the fields that we've been looking at quite a bit is this 2-meter air temperature field. We have some other fields in consideration. And also this leads into 7 spatial fields with this resolution grid, 128 times 64. And we have a paper in Journal of Climate where we did this calibration exercise using model runs and then some observational product that are shown here. And then we were considering 6 of the CAM 3.1 parameters. These are parameter names with the values range for each case. Asterisks here correspond to the default specifications, while the numbers here represent a few experiments that were performed. And then with this MVFSA approach, we generated some posterior samples using our approach, and these are posterior samples for alpha, tau, etc., for all these 6 parameters. Approximately considers 1,500 experiments are run. These are direct. This is an example again of direct simulation, direct sampling of the climate model versus using a surrogate to try to approximate the posterior distributions. Yes.
1,500 are different parameter settings.
Yes.
Yeah.
Yeah.
Okay, thank you. That's right.
Yes. Different, and this is and this here are the summaries of the different parameter settings, right? Which are generated with this Monte Carlo simulation scheme. Now the other possibility of working with this is something we're going to hear more from Dave Higdon on Tuesday or tomorrow or Wednesday, which is using a statistical emulator to approximate the climate response through a so-called Gaussian process, which is kind of like a smooth curve approximation of what the model generates, and then try to use those runs to come up with an orthogonal basis or principal component analysis basis to see to study variability, for example, across seasons, and to try to summarize this with a small number of scores, and to use some kind of modeling, statistical modeling approach that considers those observational score represented as climate, as kind of climate scores plus errors, like a climate error and a model discrepancy error. So a lot of parameters start to show up in this representation, and one has to worry about estimating this hyperparameters as well from a statistical perspective. So here, for example, is this was a first attempt that was done jointly with Dave Higdon and Jim Gattaker, who was also at Los Alamos at the time, or still is at Los Alamos, where we consider 3-year integrated runs for various seasons. This is only calibration of the TREFHT variable, the temperature variable. We did this principal component analyses and consider how many EOFs need to be used in each case to do the calibration. And this graph is based with 2,000 posterior or MCMC samples. Now, another thing we're working on, and this is with Charles and a postdoc, Mohammed Hattab, who's now in Virginia, is looking at global warming experiments where CAM 3.1 is coupled to some kind of slab ocean model. And then we have available 165 experiments or run. Some are control runs, and some other ones are such that CO2 has been doubled. And then we're looking at climate sensitivity in terms of change in global mean temperature after doubling CO2. So this is the histogram of climate sensitivity values for all these experiments. And so our approach here is to relate this sensitivity to the climate fields using some kind of EOF regression or principal component regression. We have essentially 165 data points and a big number of predictors that has to do with the resolution of the model and the number of fields that we're considering. So when we do this principal component regression, we also impose some kind of prior distribution on the parameters that define the principal component regression. This is alpha here, and then we map these parameters back to the beta space, which is the original regression representation that we have, And then we're looking at a Bayesian solution where we impose constraints on this alpha parameters through what is known as a hierarchical Bayesian prior, or shrinkage prior, where this quantities alphas are gonna constrain how many principal components are important, or EOFs are important in our analyses. So I think one of the key results here from a Bayesian perspective is that we find the posterior distributions for all this alpha. There's 165 of them, and then through the Bayesian representation we can identify which ones are significant and which ones are not significant, and decide how many EOFs we can keep to for our regression representation. So the ones in red, the ones interval. So these are estimates of the alphas and intervals, as described at the beginning, like 95% intervals, as described in this beta example. And the ones in red are the ones that are away from 0. So in some way, detecting some statistical significance on this alphas. And then when we map back to this beta space, then we start to get this regression coefficients to estimates of regression coefficients for the different fields. So we have 7 fields, and in particular for this TREFHT field, this would be our regression showing how our estimated beta or regression coefficient showing how TREFHT is in a way impacting climate sensitivity across all the map, right? Across all the globe. Want to add any comments on this slide, or you're going to talk more about this on your you're going to talk more about this problem on your session?
So I guess the background to this is that as a climate community, we don't know which errors matter to predictions.
Mm-hmm.
And so if you had an ensemble of climate models, you could go back and ask the question, what was it about the model that was important to its predictions?
Mm-hmm.
And so this is a way that you can use kind of regression statistics to inform you about the way that model is determining its properties, or that will be relevant to its predictions. So it's so that's maybe a background.
Okay, so in the computer lab session that is going to come up after lunch, so it's 12:05, so I'm going to try to wrap up and leave some time open for discussion. Essentially, it's all R and JAX models, or Openbugs models. So this is a description of the files. Have we made the files available to everybody, or how?
Quite know how
I mean, I submitted the files, and I don't know if they're already in the computer or.
No, and hopefully somebody
will
help us with that.
Okay. So there's 3 examples. One is just reproducing the binomial beta, and that's just for warm-up example to get a bit more familiar with how things work. Another one is a regression example with a time trend. So looking at temperature anomalies and doing a regression analysis on temperature anomalies to try to identify trends and estimate the model from a Bayesian perspective. This is with a data set that is already existent within R. And then the third example is a calibration example of MGCA. This is the paleoclimate application I was talking about before. and I'm going to show how it works, how we did the estimation using RJAX. But there's also a MATLAB version available of our example at this website. So when we come back from lunch, I think I will describe how this calibration works. I'll start looking at what is the data that we're considering. So 186 core top samples with global coverage. What is that we're trying to do? And there's going to be an interesting aspect to this example, which is using the model to predict temperature. So using this model that represents MGCA in terms of these variables to try to predict. So using inverse probability and then prediction to compute some temperatures, some sea surface temperatures. So I'm going to leave it at this for now, and to be continued after at what time are we meeting again? At 1? To 1?
Yeah, let's meet at 1:30 in this room.
So any more questions or comments for now? Yes.
So there's a question here.
Thank you for.
You won't hear anything. It's just going.
Okay. Thank you for your presentation. My question is, what kind of problems will be solved by MCMC, and what kind of problems will be solved by multiple very fast annealing method?
That's
I didn't get the exact answer.
Well, I think that MCMC is a really powerful tool. And I didn't know about this simulating annealing approach until I met Charles, he was the one using this method. Now the issue I have with this simulated annealing approach is that it's not clear to me that it converges to the correct probability distribution that one wishes to estimate. However, in the experience we had working with CAM 3.1, it has given us some reasonable answers. But I'm a little concerned about quantifying, say, or finding a probability interval this way with this MVFSA approach. So
maybe so the thing that I'm trying to pay attention to is whether people are able to follow along with all the ideas that are. So there's a lot of
nuts and bolts.
You're a statistician,
right?
I think most of us are not statisticians, right? At least so there's a lot of terms and ways that these ideas are need to come together, and there's ways like, let's say, a scientist would kind of summarize for themselves what's going on, and so we probably do need to help translate some of what you presented. So for uncertainty, depending on what the application is, it may be enough, like what we're doing with climate models, to have a set, let's say 20 models that represent a range of outcomes that we worry about, right? So you want those 20 samples to be good ones. And it may be, why do you only have 20? Well, maybe because the model is so expensive you can't afford thousands, right? And so this is a little bit what's forcing this situation, right? Is that we have only a limited ability to collect samples. The other thing is that in the statistics community, when you come to large-scale problems, often you can reduce the cost of this exercise by coming up with a what's called a surrogate model, which basically stands in for your complex model. And this is what Dave Higdon will talk about. The Gaussian process is a way of predicting what a climate model would have done if you actually ran it. and you can make that predictions based on maybe a set of collections that are kind of well-designed experiments, and basically the emulator will interpolate in this multi-dimensions what that model would have done.
Now I have to say also from the statistics perspective that these emulators are not necessarily easy to fit. Right? This is statistical emulators.
That's right.
are also complex. I mean, they're not as complex as the climate model is, but they're also complex. I mean, they have a difficulty to be estimated.
So, in that, it's not clear to me that we have emulators for something as complex as a climate system model, and there are ways you can get around it, and maybe there can be some discussion, because I think the Hadley Center has a way of thinking about this and implementing it, and that like some of what Gabriel was presenting is my point of view, but is not necessarily the universal point of view on this. And this is that what we need is versions of a model that are equally scientifically valid, that would make that shows the impacts of being uncertain about what parameters you're setting in the model, and therefore you're getting a distribution. So the statisticians tend to worry about whether the probability distribution is well sampled,
right,
has beautiful tails, and and as a climate scientist, I'm not so worried about that. I'm worried about that the versions of the model that I'm working with are scientifically valid, that they represent a range of outcomes that we should be considering. And that was a little bit motivating me in the strategy that I had with simulated annealing to pick an ensemble that I thought was credible. But I would say it's atypical from a statistics community to take such an expensive model and find different versions of it directly. So that's a little bit an answer to the question earlier.
So the first part of your summary, when you said you can only have maybe a couple of 10 good runs and you want them to be good.
Yes.
So there's two meanings to good. So there seems to be two meanings to good. One would be that those 20 versions are, sorry, so there's like the question of whether your model is scientifically valid, and then the question of whether you're correctly sampling some kind of PDF, but what PDF is that? Of what? A PDF of what?
So the PDF representing the alternate versions of the model that could have been developed. Let's say, so a climate modeling center will develop a climate model. They will pick one version.
Yes.
What you would like to know is what other versions could they have developed if they had more resources to span basically what every reasonable person would have chosen. You know, let's say you have some metrics that you're trying to do. A good climate model will have the right distribution of precipitation and so forth. And you have many different competing interests in the use of that model. And there might have been, let's say, so usually we think of parametric uncertainty, which is let's say the main source of uncertainty is clouds. And so people may focus on the 10 or so parameters that are important to predicting that model's clouds. And but the question is, what combination of alternate parameters would give you a reasonable climate? And this is where uncertainty quantification tools can select the combination of those 10 parameters that will still yield a good model.
But could not be scientifically sound. So you could have a combination of parameters that would give you a reasonable climate, but that would not be physically sound.
You definitely want to make sure that this process doesn't give you unsound samples. And so we're still working this out. And it could be that the versions of the model that we have are not good. But let's say from a science point of view, you wouldn't want to look at them.
But they give you a good climate.
Yeah, that's right. So you want to have samples that give you, let's say, climate for the right reasons, rather than the data that we observe for the wrong reasons. And we're still in the process of knowing how to make use of, let's say, uncertainty quantification tools to give you a distribution of scientifically useful models. We don't know if we are capable of doing that. Let's say we have scientists who look at these things, and we are generating these ensembles, but there is this risk, and I think this is probably the primary concern among scientists, is that if we start using these these things which we don't have good scientific intuition for selecting our models, we may be doing something that we shouldn't be doing. So I think it's a very good comment.
There's also another question. There's also.
Okay, so I like this discussion, so I skip out on lunch. Go ahead.
Well, so if I'm understanding you well, this analysis could be used to pick different parameters that are appropriate for a climate model.
Mm-hmm.
But why then do you need distributions? Why not use very simple approaches, or maximum likelihood approaches? Why do you need really the full PDF? Wouldn't you find the same results? If you're only looking at the mean of the distributions, or at the peaks of the distributions.
Did you hear the question, Ben?
So are you contrasting the maximum likelihood to the PDFs you're talking about?
Yes, because well, the presentation was about distributions,
Right.
but in the end, you only look at the peak at the maximum of the parameters. So
you can imagine lots of situations where you might be interested in what is possible, but less likely. So if you're interested in load management, for example, you might be interested in what are the high-end rainfall events
yes,
that might occur.
okay,
Less likely. So there are different users. I think some users want to know most likely.
okay.
Some users want to know what the table.
So
Okay, so you're also using the whole distribution to
Right.
to make, for example, to quantify the uncertainty in the future. But then I would think there is a problem, because you do this analysis given 5 parameters, for example, and you reduce all the uncertainty that you have, which was listed by Chris Forrest, to the uncertainty coming from these 5 parameters, and I wouldn't think that this is realistic.
Yeah.
I think
So
this is
how do
a
you-
great question, but may take a longer time to discuss. We have discussing session every day afternoon.
Not this
So
afternoon.
Yeah, not this afternoon, but we will discuss later.
Mhm.
But we have to stop here now.
You think we should eat?
Yeah. We'll come back to this room 1:30. So.
Oh, this room, not the. Oh. Oh, okay, okay, okay.
And now you have to stay here. We have the technician to try to discuss the
Part-
software.